congruent to each other, then we can say T1 is congruent to T2 as well as T2 is congruent to T1. We find an element in the form of A comma B, but we cannot find an element in the form of B comma A because we have 1 comma 2 but we don't have 2 comma 1, hence it is not symmetric. If I take any one of the lines here, it cannot be perpendicular to itself. Remember, every line is parallel to itself but it cannot be perpendicular to itself. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Vidhyaashram School of Excellence, Mysuru. In our previous session, we have discussed the types of relations. What are the types of relations we have learned? That is reflexive relation, symmetric relation, transitive relation. When all the three holds for a particular set of relation, then it is called as an equivalence relation. Let us see few problems or few examples and verify whether it is reflexive, symmetric, transitive, or is it an equivalence relation. So the very first problem is here. Show that the relation R in the set of Z of integers given by R is equal to A comma B 2 divides A minus B is an equivalence relation. Observe that here the relation is in the set of integers and we already know that A minus B will be an integer. Obviously it is an integer and 2 divides A minus B means it must be an even number. Whether it may be a negative plus or minus 2 plus or minus 4. So here we also consider 0 as an even number to prove this relation as an equivalence relation. What is the first thing we have to do? We have to show that it is reflexive, it is symmetric, it is transitive and hence it is an equivalence relation. So here let us prove the first result. Let me write 2 divides 0. Why I am writing 0? Because 2 divides A minus A. Suppose you take the set of integers in the form, because for a reflexive, A comma A must belongs to R. This condition must be satisfied. To show that A comma A belongs to R, we have to show that 2 divides A minus A. So A minus A becomes 0 and 0 is in the set of integer. Hence we can write this implies A comma A belongs to R. So whenever for all A, for any integer, for example, if you take 3, then 3 minus 3 is in the set Z. Hence we can write 3 comma 3 contains in the set of relation. So therefore R is reflexive. Now let me prove that it is symmetric. So to show that symmetric, let us consider A comma B belongs to R. If A comma B belongs to R, what does it imply? It implies 2 divides A minus B. See, if 2 divides A minus B, we can also write 2 divides minus of B minus A, because it is also an example for an integer. So here suppose I write 2 divides 4 minus 2. 4 minus 2 is 2. Hence we can write 2 divides 2. So 2 also divides 2 minus 4, which is minus 2. If 2 divides 2, then 2 also divides minus 2. Hence if 2 divides A minus B, then we can write 2 divides minus of B minus A. So this implies what? 2 divides B minus A. If 2 can divide minus of B minus A, then it also divides B minus A. So once if you write 2 divides B minus A, we can conclude that B comma A belongs to R. See here, for all A, B in the set Z, if A comma B belongs to R, we are getting B comma A belongs to R. So therefore, what I can conclude, R is symmetric. The next one is we have to show that it is transitive. So for that, let me take 2 ordered pairs. A comma B belongs to R and B comma C belongs to R. What does this implies? If A comma B belongs to R, 2 divides A minus B and 2 divides B minus C. So if 2 divides A minus B, 2 divides B minus C means obviously A minus C and B minus C are integers. Hence, I can write this as 2 divides A minus B, add these two plus B minus C, because the sum of two integers is also integer. Hence, we can write if 2 divides A minus B and 2 divides B minus C, we can write 2 divides A minus B plus B minus C, which implies 2 divides A minus C. Once you got 2 divides A minus C, what we can conclude? We can conclude the ordered pair A comma C is in the R. So for A comma B belongs to R, B comma C belongs to R, we are getting A comma C belongs to R. So therefore, R is transitive. So now we got R is reflexive, R is symmetric and R is transitive. So therefore, what I can conclude, R is an equivalence relation. So the very important questions which will be asked for 3 marks question, you have to show that R is reflexive, R is symmetric and R is transitive to prove that R is an equivalence relation. Next question, show that the relation R in the set A, X belongs to Z, 0 to 12. So here the set A contains the numbers from 0 to 12, 0, 1, 2, etc. until 12. All positive numbers along with 0 until 12. Given by A comma B, modulus of A minus B is a multiple of 4, is an equivalence relation related to 1. Find the set of elements related to 1. We have to show that A comma B is a multiple of 4. So, what are the elements, what are the ordered pairs we can write such that modulus of A minus B is a multiple of 4. So, here they have given if A comma B belongs to R, then we can write mod A minus B is a multiple of 4. So now let us show that whether it is an equivalence relation or not. Now first one, so here I will take 0 is a multiple of 4. So how we can get 0? We can get 0 in the form of mod A minus A is a multiple of 4. Because 0 is in the set A. So, if we have any element, if we have 1 in the set A, then 1 comma 1 should be in the set R. To show that 1 comma 1 is in the set R, we have to show that it is a multiple of 4. That is 1 minus 1. Since it is 0, it is a multiple of 4. So, therefore, for any elements like 2, 3 until 12, all the elements in the form of 3 minus 3, 4 minus 4, 6 minus 6, 7 minus 7, you will get 0, which is a multiple of 4. So, therefore, what we can conclude, we have an element in the form of A minus A, which is multiple of 4. So, this implies what? A comma A belongs to R. So, therefore, R is reflexive. Similarly, to show that it is symmetric, we have an element A comma B belongs to R. This implies modulus of A minus B is a multiple of 4. Is a multiple of 4. So, this can be written in the form of modulus of B minus A. Again, you will get a positive since you have modulus. Therefore, we can write B minus A is also multiple of 4. So, if modulus B minus A is a multiple of 4, what does this implies? It implies B comma A belongs to R. So, for A comma B belongs to R, we have B comma A belongs to R. So, therefore, what I can conclude? R is symmetric. Next, we show that R is transitive. So, let me take two ordered pairs. So, A comma B belongs to R and B comma C belongs to R. So, this implies what? Modulus A minus B is a multiple of 4, is a multiple of 4 and modulus B minus C is a multiple of 4. So if these two are possible, then I can write it in the form of A minus B plus B minus C is a multiple of 4. So hence I can conclude mod A minus C is a multiple of 4. So therefore what I can conclude, A comma C belongs to R. So therefore we can conclude R is transitive. Hence for A comma B belongs to R, B comma C belongs to R, we are getting A comma C in R. Therefore R is transitive. Hence R is reflexive, symmetric and transitive. So therefore I can conclude R is an equivalence relation. It is an equivalence relation. Now we have to find the set of elements related to 1. That is, we have to find the other element in the form of an ordered pair. That is, we have to show that 1 comma B belongs to R. This implies modulus 1 minus B is a multiple of 4. It's a multiple of 4. We have to show that modulus 1 minus B is a multiple of 4. Then what are the elements I can take in the form of 1 minus B along with 1? So we have an elements 0, 1, 2, 3, 4 until 12. What are the elements I can pair with 1? So I can pair 1, 5. Because 1 minus 5 is minus 4, modulus of minus 4 is 4, so 4 is a multiple of 4. Next I can pair 1, 9. So 1, 9 because 1 minus 9 is again 8 minus 8, modulus of 8. Hence, along with this I can also write 1, 1 because we have already proved that A minus A is a multiple of 4. That means 1 minus 1 is also a multiple of 4. So therefore the elements which I can pair with 1 is 1 and 5. So therefore the elements related to 1 are 1, 5, 9. So these are the elements I can relate to 1 so that it is a multiple of 4. Next question. Let T be the set of all triangles in a plane with relation R given by R is T1, T2. The condition is T1 is congruent to T2. Show that R is an equivalence relation. Now, let us show that we have a set of all triangles in the relation R where T1 is congruent to T2. That is, the triangles are congruent to other triangle. So, if I write T1, T2, then T1 is congruent to T2. We know that all triangles are congruent to itself. So therefore I can write T1, T1 belongs to R. So therefore R is reflexive. Next is second one. If I take T1, T2 belongs to R, this implies T1 is congruent to T2. If two triangles are congruent to each other, then we can say T1 is congruent to T2 as well as T2 is congruent to T1. So therefore, this statement can be written as T2 is congruent to T1. So this implies what? We can write T2, T1 also belongs to R. So therefore, R is symmetric. Next we take three triangles. Let me take T1, T2 belongs to R and T2, T1 belongs to R. So here if T1, T2 belongs to R, this means what? T1 is congruent to T2 and T2, here we'll take T3, T2 is congruent to T3. So T1 is congruent to T2, T2 is congruent to T3. So this implies what? T1 is congruent to T3. So if I have three triangles such that T1 and T2 are congruent to each other. So this is T1, this is T2 and T2 is congruent to T3, triangle 3. So this is T3 I can take. So if these two are equal in size and shape, then these two are equal in size and shape, but then obviously T1 and T3 are equal in same size with same shape. That is, they are congruent to each other. Hence I can conclude T1, T3 belongs to R. Therefore, R is transitive. Now, R is transitive. So, therefore, I can write R is an equivalence relation. Next question. Let L be the set of all lines in a plane with relation R defined by L1, L2. L1 is perpendicular to L2. So, perpendicular to relation we have to define. Show that R is symmetric but neither reflexive nor transitive. So, here we have a set of all lines L. There may be many number of lines which are parallel, some are perpendicular, anything like this. It's a set of all lines. So, here we have to show that the relation perpendicular to is symmetric but neither reflexive nor transitive. Now let us show that the first case, reflexive case. We know that a line cannot be perpendicular to itself. So therefore, what I can write? Every line cannot be perpendicular to itself. So, perpendicular means the angle between the two lines must be 90 degree. But here, if I take any one of the lines here, it cannot be perpendicular to itself. Remember, every line is parallel to itself, but it cannot be perpendicular to itself. So, therefore, there do not exist any lines in the form of L1, L1 belongs to R. That is, there is no A, A belongs to R. So, therefore, what I can write? R is not reflexive. Now, next let me take two lines. L1 and L2 belongs to R. If L1 and L2 belongs to R, it means L1 is perpendicular to L2. Consider these two lines here. So, suppose I take this is L1 and this is L2. If L1 is perpendicular to L2, then I can say L2 is also perpendicular to L1. So, that means I can write L2 is perpendicular to L1. If this condition satisfies, then I can write L2, L1 belongs to R. So, I am getting here for L1, L2 belongs to R. We also have L2 and L1 belongs to R. So, therefore, I can write R is symmetric. Now, let's see about the transitive relation. See, I already said you there is a number of lines here. Suppose I take three lines, L1 perpendicular to L2 and L2 perpendicular to L3. So, let me draw a lines here. So, we have this is L1 and this is perpendicular to L2. Now, let me take one more line, L3. So, here L1 perpendicular to L2. So, this is line L1 and this is perpendicular to L2 and L2 is perpendicular to L3. So, is it L1 perpendicular to L3? No, this is not possible. So, let's write here L1, L2 belongs to R and L2, L3 belongs to R. So, this implies what? L1 is perpendicular to L2 and L2 is perpendicular to L3. But L1 can never be perpendicular to L3. So, this is not possible. That means L1, L3 does not belongs to the set R. That is not in the set of relation. So, therefore, R is not transitive. So hence we have shown that the set of all lines in the set L and a relation perpendicular to is only a symmetric relation, but it is neither reflexive and nor transitive. Next question, give an example of a relation which is transitive but neither reflexive nor symmetric. Now I can give any example in the form of to show that it is transitive. So I can write a set of relation in the form of 1, 2, 2, 3, 1, 3. So I can take this is also an example for a relation which is only transitive but not symmetric, not reflexive. We don't find any element in the form of A, A, therefore it is not reflexive. We find an element in the form of A, B, but we cannot find an element in the form of B, A because we have 1, 2 but we don't have 2, 1. Hence it is not symmetric. So I can give a set of relation, any example or any relation to show that it is a relation which is only transitive but neither reflexive nor symmetric. Next one, give an example of a relation which is symmetric but neither reflexive nor transitive. See the relation perpendicular to. Relation perpendicular to. We have already proved that this is an example for a symmetric, but it is neither reflexive nor transitive. Every line cannot be perpendicular to itself, so therefore it is not reflexive, and 3 lines cannot be perpendicular so that the L1 and L3 are perpendicular to each other, so it is neither reflexive but it is symmetric. So the relation perpendicular to is also an example for a symmetric relation but neither reflexive nor transitive. We can also give an example of R is equal to 1, 2, 2, 1. See, this is the set which satisfy only the symmetric relation. We have 1, 2 in R, so 2, 1 is also in R, hence it is symmetric. But neither reflexive, we don't find any element in the form of 1, 1 or 2, 2, so therefore it is not reflexive. We don't find any element which satisfy the transitive property also. Hence, this is also an example for only symmetric relation, but neither reflexive nor transitive. So next question we have. Show that the relation R in the set R of real numbers defined as R is equal to A, B, A less than or equal to B is reflexive and transitive but not symmetric. See, here we have taken in the set of all real numbers. So for the first case, to show that it is reflexive, we can write 1 less than or equal to 1, we can write 2 less than or equal to 2, we can write half less than or equal to half, like this. So for all the real numbers, the condition satisfies. That is, A less than or equal to A is true for all real numbers. So therefore, this implies A, A belongs to R. So therefore, R is reflexive. Now to show that it is symmetric. Symmetric means what? If A, B belongs to R, then B, A should belongs to R according to the given condition. Suppose I write 2 is less than or equal to 3, then 2, 3 belongs to R. But I cannot write 3 is less than or equal to 2. This is not possible. So therefore, if A, B belongs to R here, this implies A is less than or equal to B. But B less than or equal to A is not possible. So therefore, B, A does not belongs to R. Therefore, R is not symmetric. Now, given it is a set of our real numbers. Now, let us show that whether it is transitive or not. We have to show that it is transitive but not symmetric. So here, if I say any real number, 1 is less than or equal to 2, 2 is less than or equal to 3, then obviously I can write 1 is less than or equal to 3. So this is possible. Hence, if A, B belongs to R and B, C belongs to R, This implies what? A is less than or equal to B and B is less than or equal to C. This implies A is less than or equal to C. Therefore, A comma C belongs to R and hence I can write R is transitive. So hence we have shown that the set of the relation A less than or equal to B is reflexive transitive, but it is not symmetric. Next question. Show that the relation R in the set of R real numbers defined as A comma B, A less than or equal to B square is neither reflexive nor symmetric nor transitive. So this is just an example for a relation, but it is not a reflexive relation nor symmetric relation nor transitive relation. So here clearly, so A less than or equal to A square is not possible for all values in R. Not possible for all values. We can write 1 less than or equal to 1 square because it is equal, but we cannot write 2 less than or equal to 2 square because 2 less than or equal to 2 square means we have 2 less than or equal to 4. Suppose I write half less than or equal to half square. Another example, here I will get half is less than or equal to 1 by 4. This is not true, this is false. So here it is true. For this case, it is true. But in the case of fraction, this is not possible. Hence, it is not possible for all values in R. So if it has to be true for all values in the set, then only I can write the ordered pair A comma A belongs to R. But here it is not possible for all the values in R. Hence, this is not a reflexive relation. Therefore, R is not reflexive. So similarly, for the second one, if A comma B belongs to R, this implies A less than or equal to B square. But B less than or equal to A square is not possible. You can take by taking counter example using numericals also. So this is not possible. So therefore, R is not symmetric. Now let us prove the third one. Suppose I have A comma B belongs to R and B comma C belongs to R. Then according to the definition of the relation set, it is A less than or equal to B square and B less than or equal to C square. So again here also A less than or equal to C square is not possible for all values. It is only possible for few values as in the case of reflexive. Hence, it is not possible for all values in the set R. So, therefore, I can write R is not transitive. Hence, the set of a relation in the form of A less than or equal to B square is neither reflexive nor symmetric and not transitive. Hence, we have proved it. So, as in the case of many relations that we have showed, whether it is reflexive or not, whether it is transitive or not, whether it is a symmetric or not, or whether it is an equivalence relation, we can take any number of relation set to verify these properties. This is all about the types of relation. We'll continue in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.